Hi, I'm Taohan Wang. Today we want to talk about our recent project, a star-based MPC for vehicle path planning and simulation. This is our working outline. First, perception, data conversion, A-star path planning, MPC dynamics model and constraint, MPC reference tracking, simulation result and conclusion, future work and reference. How cars see the world. Here are 4 ways. Camera, LiDAR, radar, and maps. LiDAR is especially powerful at precisely localized objects. This is why we choose LiDAR to do object detection. This image is a visualization of a 64-beams laser data. All the points are described in Euclidean coordinate system. However, it is hard and inefficient to cluster the point cloud data directly on Euclidean coordinate system. Instead, we need to find another way to interpret those points. We project those points to form a range image, and we call this kind of picture depth image. Next, we are going to find objects through depth image. The basic idea to extract an object is to find its edges. Here, we pick up a column from the depth image to illustrate our method. From the bird view of this column, we notice that the point can be divided into 3 parts: red, blue, and green. Then, we pick up 2 neighbor points. In this case, it's A and B. Then we link those 2 points to the origin from OA and OB. Draw BH perpendicular to OA. From HB and HA, the beta angle can be calculated. As the picture shows, if the points are near each other and belong to the different clusters, the beta angle will be small. Based on this algorithm, we can find the edges of the objects. With all the detected objects, the result is look like this. Blue boxes are the detected objects, and the green area is the drivable region. Next work is about data conversion.
Hi, this is Jiayang speaking. In this project, I worked on the data conversion from the cloud point to the MATLAB, and I also helped in the path planning. So, after we get the LiDAR data, we need to convert them from the point cloud to a matrix format which can be used in MATLAB. Let's call this picture a map. In this map, you can see the boundaries of the crossroad obstacles like moving cars and barriers. In MATLAB, we create a 100 by 100 matrix representing all coordinates in the map, and a value of 2 at a point means this region is free. A value of -1 means the host vehicle cannot go onto it. We call this matrix a map matrix, and the figure above is a contour plot of this map in a certain time frame. All these greenish lines actually represent the gradient from -1 to 2. It is very steep in order to mark that boundary very clearly. Each matrix is for 1 time frame, and we have 461 matrices in total. Let me give you some more details on this conversion. For the crossroad boundaries and barriers, we get the coordinates from the cloud point and simply transfer them into the map matrix. However, for the obstacles, like moving cars, in the cloud point, the code only gives us the coordinate of a vertex of each obstacle, and we convert it into a circle with a radius of 2.5 meters to represent a moving car. However, the pure conversion is not enough in our case. Since we want the host vehicle, for example, to make a smooth turn without collisions, we need to leave some space between the host vehicle and any potential obstacles, like the boundaries, barriers. So we increase the size of the barriers, the moving cars, and the map boundaries to incorporate that safety region into our system. Now we have all the data ready to do the actual path planning.
Hi, my name is Anke Zhang. In this project, I'm taking charge of implementing A-star algorithm, and this method can find paths between 2 points based on some cost functions, as long as these 2 points are connected in the map. this is a dynamic programming method, which means for every subproblem, the children's cost is based on the parents as the program progress. This problem, this algorithm is much faster than brute force because it can find the path between 2 points without going through all the points in the map. However, this algorithm requires a cost function that is convex in order to give a meaningful result. In A-star algorithm, we start from the starting point. In here is S0, and we add S1, S2, and S3, which is S0's neighbors, into a cost list. And the parents of these three neighbors is S0. And we calculate all the cost of these 3 points and add to the list. And then we dequeue the node with the lowest cost. In here is S2. And then we add S2's neighbors, S4, S5, and S6 to the list. And by the same time, we calculate the cost of S4, S5, and S6. And then for now, like S4, S5, S6 have all the parents to be S2. And then we just keep repeating this process until we find the ending point, which is like a Sn with some cost. And then after we find this point, we just trace back to the parents to S0, and we can find a path between S0 and Sn. If all the point is searched and no ending points shows up, it means this problem is infeasible and we cannot find the path.
This is Moyu speaking. For path planning, we implement cost functions for the A-star search algorithm. For obstacles, including boulders between roads and other moving cars, they don't have a cost function defined, as shown in the picture. The cost function is decreasing when the distance to the target point is decreasing. We add another cost function based on the ideal trajectory, shown as the red curve in the picture. The cost function is decreasing when the distance to the ideal trajectory is decreasing. We adjust the weight for the two cost functions and we add them together so that the cars moves in a relatively short distance and turns smoothly. In this slide, the result of the path planning is shown in the trajectory as the blue curve. As you can see, the blue trajectory takes in a relatively short distance and takes the turn smoothly. This optimal path is used as a reference path for the MPC later. The path planning is done in real time at each time step. If a vehicle moves through the trajectory, the path planning algorithm will search for a new optimal path at that time step.
Our teammates have done the path planning. Now it goes to the MPC preparation section. I am Ming-Hsueh, who take care to figure out the system modeling and its constraints. In this slide, instead of applying a complex physical model, I inherit the model which is used in our homework 4, named bike FE, this M file in the parking problem. As what you see in this slide, the input is the acceleration of the center of mass into the direction, and the other one is the angle of the current velocity with respect to the longitudinal axis of the car. and we will import this input into our cloud FE model so that we can get the output. The output includes the first two parameters are the global coordinates of the vehicle, which are x and y. Another is v, which means the speed of the vehicle, and the final one is the heading angle. In the car FEM file, this system itself, we keep parameters that are same as what we use in the homework, but define the sampling time is 0.1. Now we finish the section of the model setup. Then I switch to the next slide, the definition of the cost function we will use. Before defining our cost function fitted into our MPC, we need to clarify the constraint first. By discussing with our teammates, we decided to use the real data of the car named Lincoln NKZ, this car. And this data comes from one of our teammates, Wang Taohan, about the setup of the Z minima, Z maxima, and the input U minima and the U maxima. I try to look for the reasonable value reflecting to our real driving situation. So we could see why these numbers of the constraint are defined in this slide. For the cost function definition, I apply the common used one and give the Q and R shown in the slide, which means to penalize for the deviation from the reference trajectory in both x and y direction, and also penalize our input signal. Here, I finish the preparation for the MPC and pass the information of the model and the constraint data to our teammate Jialong to run the MPC trajectory reference tracking.
Hi, I'm Jialong Ren. After setting up the dynamic model, the constraints and the cost functions, we started to use the MPC to generate the optimal path that tracks the reference path. We use 10 as the MPC horizon and 70 as the simulation horizon, and select IPOPT as YAML solver. This plot shows the optimal path generated by the MPC versus the reference path. As we can see, the MPC path tracks the reference pretty well, and the generated path is much smoother than the reference, which means that our MPC successfully gives us an optimal path with a very low cost. And this video is a demo for the vehicle going along the path generated by the MPC. We can see that the vehicle makes a very smooth and safe right turn without the danger of running into the obstacles. So the results of our A-star based MPC algorithm is quite satisfying. And in the future, we think our projects can be improved in two ways. First, we should try the cases with more complicated scenarios. For example, if our vehicle is going to change a lane or overtaking other vehicles. Second, we can tune the numbers of the cost functions for both the A-star algorithm and the MPC, so we can find a better path with lower cost. This is our project. Thank you for watching.